Welcome to our lectures on NPTEL on power quality improvement technique. We shall discuss on the UPQC classifications. So, we have seen the classifications. Now, we have in our previous class, today we should talk about the system based classification of the UPQC. And there are many consumers loads such as domestic appliances connect to the single phase systems. Some 3 phase consumer loads are without neutral terminal, such as adjustable speed drive from the 3 phase 3 wire systems. So, that generates, these are the source of the harmonics. Hence, UPQC may also be classified according to the, because we require to put the UPQC where most problem arises. So, you have to put at the point of the bleeding, that is called banded method. So, according to the supply, this is the issues. So, for this reason the classify is according to the supply system as single phase 2 wire, we have discussed in the chart in detail in our previous class, 3 phase 3 wire UPQC and the 3 phase 4 wire UPQC. The number of configurations we will discuss now little of single phase 2 wire, 3 phase 3 wire and 3 phase 4 wire system UPQC are given for the enhancement of the power quality in the current as well as the voltages. So, that is something we require to ensure, we require to get a proper, we require to find it out what is the source of the harmonics or the disturbance or anything. If it is due to the adjustable speed drive in a 3 phase 3 wire system, we should choose UPQC very close to that pollutating load, and ultimately we have to keep their problem localized and does not allow to propagate this problem to other part of the power system. Now, and thus we have a 2 wire UPQC, which is a single phase UPQC. So, UPQC are used for both right shunt and the left shunt. Since voltage rating does not vary much because it is a single phase system. So, for this reason we do not have much complexity, we can use, as far the rating is concerned, we can use right shunt as well as the left shunt. Both converter configurations, a current source inverter with the PWM modulation technique having inductive energy storage elements, and the voltage source converter with the PWM control having capacitive DC bus energy storing element are used to form the 2 wire circuits. Generally shunt is a inductor, and generally you got a series injection that generally sink through this little power from the shunt path, and you send it this power from this DC link voltage, thus it is generally capacitive. In case of the DVR with the voltage source converter, sometime the transformer is removed because it may be a very small rating is removed with the consumer load shunted with the L and C component, that is also a configuration. So, see that this is a configuration. So, ultimately you got a D statcom. So, here mainly this capacitor is charged through this path, and if there is a sag, then it required to inject the voltage, and this voltage is been injected. So, power will generally flow from this side, and if there is a swell, so it will take out the power and this capacitor voltage will swell ultimately. So, this power has to go back to the system from the shunt path. If it cannot do that, then we require to provide a beater resistor to take this resistance, to switch it on this resistance and ultimately reduce the rating of the capacitor, and you have a critical load. This is a single phase UPQC solutions, mostly it is comes with the adjustable single phase adjustable application. For example, you may have a lifts and little lifts of we, because nowadays we require we want that the movability of the disabled in everywhere. So, you want the lift, and maybe a old building, so does not have a proper grounding and lift. So, you have a different kind of 1 man 2 man lift, and that rating can be up to the maybe 3 kilowatt. So, there, but it may be adjustable speed drive, and it happens to my institute itself. We have it is an old building around 60 years around 70 years old, and we have put the lift for the mobility of the disabled, and and there we have adjustable speed drive also, and we require to mitigate, because this is a source of the harmonics, by this single phase UPQC. So, these are the discussion has to be followed. Now, we talk about the more common UPQC that is been placed, because loads are around 10 kVA to 100 kVA, and thus rating of the UPQC will be in that range. The 3 phase 3 wire consumer loads such as adjustable speed drive, for example, smalls and all, you have multiple lifts operating, or maybe a big buildings such as ASDs are one of the major constituent of the 3 phase loads. Classical VSC based configuration of the 3 phase 3 wire UPQC is most common configuration of the UPQC. Sometime an isolation transformer is also used to isolate the shunt device D-STATCOM of UPQC in high voltage rating application to design power converter at optimum voltage and the current rating. So, this is something what we have seen that S. So, we can design that different way. We have sometime a constraint of the power quality. So, we require a power quality, and no one will say that enough money is available. So, we require to have a optimization somewhat. So, it may be have a rating optimization, and thus the component cost optimizations, BOM optimization, or sometime we may go for the rating optimization in this. So, this is a different kind of constraint can be put by the supply engineer. Accordingly, engineers have to design it. The DC capacitors is connected in the DC link of the VSC of the D-STATCOM, and its voltage is maintained at the desired level by the controller, desired relevance of the reference receivers voltage VDC, by controlling the voltage source controller of the D-STATCOM. Generally, capacitor required to be maintained little higher. I just go back to the it is same for the single phase system. This capacitor voltage required to be maintained little higher, so that the power can sink through it. So, that ultimately what happened, we require to inject current to this point. For this reason, we require to inject power if there is a leading power factor. The VSC is connected using a interfering inductor. It is very simple, because generally this VSC is generating the PWM pulses. So, you got this kind of pulses of variable width, and maybe your compensating current is of this natures. So, for this reason there is and also the point of common coupling where it is connected, this shunt part, it is something like this. So, for this reason what we require to do, we have a instantaneous voltage difference between these two, and current required to be maybe this. So, thus we require a interfacing inductor, which will act as a buffer between the VCC, VSC, that is voltage source converter, and this is the voltage at the point of common coupling for the shunt path, because I assume that already voltage has been injected by the DVR, and thus it is got a pure sinusoidal, and current, it may be compensating maybe the harmonics, and current required to be injected by the shunt part is this. There is a ripple filter CF and RF connected at the load terminals of the UPQC in order to filter the high frequency components of PWM voltages from the VSC to the STATCOM. The VSC of the DVR is connected at the same DC-link of the VSC of the T STATCOM, and it is connected in series with the AC mains using the AC injections. So, this is a way of operation of the T STATCOM. And moreover, the ripple filter, the LR and CR is used for, because it is a switching. So, generally it is switched maybe IGBT, that is switching maybe at 10 kilohertz. So, those switching ripples required to go out, ultimately this is not a big challenge, because ultimately your power system is a low pass filter, is used to filter out the high frequency component of the PWM voltage from the VSC of the DVR. So, this is the overall structures of the 3-phase 3-wire UPQC. So, these are DVR, as I told you, these are the LF, because you got a instantaneous difference, and ultimately you have to mitigate the switching ripples. So, for this reason you have a small capacitors and LF. So, those will damp out those frequencies. Ultimately this L and this C will have a resonance frequency at a very close to your switching frequency, and it is passively damped also by the resistor RF, or it may be the physical resistance is not connected, it may be due to this series resistance of the inductors and the capacitor is been put into the lump parameter as RF. Similarly, we have this series injections for the LR, and we have a DVR and CR, and there is a leakage reactance that will mitigate your switching frequency ripples, and that will be sank or mitigated, damped actively by the RR resistances. So, this is the principle of operations of the 3-phase 3-wire 2-level UPQC. Similarly, we have a problem of the neutral current, and thus we have a problem of the unbalanced. So, for the, and we wanted to compensate, instead of putting the 3 single phase unit in each phases, we will require to combine, and we will put it as a 3-phase 4-wire system. So, thus what happen, a large number of single phase load may be supplied by the 3-phase main with the neutral conductor, and all are maybe polluting, maybe you have a inductive load, maybe you have a adjustable speed drive and so many adjustable speed drives, and also you have a problem of the unbalanced current, that is the neutral current. The excessive the cause of excessive neutral current, that is what I am saying. Harmonics, there is maybe a source of the harmonic reactive power burden as well as unbalanced current. If there is a unbalance due to the voltage, it is very difficult to clean up by this shunt path. We assume that it is not there, DVR already compensated. But anyway, in that case, as since DVR is integral part of this system in case of the UPQC, so it has been cleared up. To mitigate this problem, a set of the 3-phase 4-wire UPQC is used. So, bundle of the problem, you just put a one single solution. This is the way, and for this reason we generally do we have studied load flow equations. There is a harmonic load flow we require to do for the 5th harmonic, we have to do for the 7th harmonic, and thus what you do in a load flow, you find it out the maximum sag point. Same way here you require to find it out in many bus, which bus has maximum power quality problem in case of the harmonic, and thus you have to put it to its saddle point, this UPQC. So, that itself is a topic of research. So, to mitigate the problem, a set of 3-phase 4-wire system UPQC is used. The UPQC have been developed in many configurations. Configuration may be there a single phase VSC by UPQC, which is quite common in this version, allows the proper voltage match for the solid state devices and enhances the reliability of the UPQC. So, this is the where you will apply the 3-phase 4-wire system, and mostly its rating is little less because voltage is 4-wire system is 440 volt and current cannot be very huge, and for this reason it is limited to around 100 kilowatt. And now this part was common for the 3-phase 3-wire system with the 3-phase 4-wire system. You got an extra switch, extra legs sorry, in case of the 3-phase 4-wire system, and this is for the neutral wire compensation. So, you require to have another entity extra. Otherwise, there is another topology can be used, that you can split this link and you can put this 4th wire on the middle of the DC link, but there is a problem that it is not controllable. Current will flow as it is, but and also the performance of the performance of this unbalance cannot be checked also, and for actively controlling the neutral current we require to have a 4th leg. So, thereafter so this is a rating based classification of the UPQC. The 4th classifications of UPQC is based on recently reported method. So, it is not very recently reported, rather 20 years ago, that is the UPQC Q, it mainly compensates the reactive power, and UPQC P, it mainly compensates the real power, and UPQC S, its KVA rating is constant, you have a flexibility, use either P or Q. These different types of control methods affects rating of the converter of the UPQCs. The voltage sag on the system can be compensated through the reactive power control and the reactive power control methods, because you may make it a capacity compensation, that what has been done by the overexcited synchronous generator. Same thing you can achieve by the sag control. So, what happen, you have a voltage, you inject the voltage by 90 degree, you got this voltage. So, but problem lies, your current has to be compensated accordingly, that is a part of the shunt path. So, in case of the UPQCQ, we will show you the next slides detailed discussions of it. The shunt compensator D-STATCOM is normally connected across the consumer of the load end and the right shunt of the UPQC. This D-STATCOM is used for all current based compensation at the load end. So, this is the case. Now, you had this is a voltage and you inject the voltage at quadrature, and thus you got a new voltage here, and ultimately and you got a compensation where it will make this SL equal to L, and you got a new angle, it was initially phi, now it will be delta. So, let us explain it. In this Q, in such a situation, the series compensator DVR inject voltage in series between the AC mains and the load in quadrature with the supply current, and needs only the reactive power from the DVR, which generally it is generated by switching without any active power injection through the DVR with the accurate or adequate injection. The phasor representation of the voltage sag compensation of the reactive power is shown in this figure. So, ultimately you had initially Vs and this was a VL, you inject the voltage 90 degree to it, this is a DVR voltage and new voltage will be this, and by compensations by current it will try to make the sinusoidal. And also there is a harmonic component that also required to be mitigated, not only the power factor. Now, UPQC based on P. So, you will have a voltage DVR. Now, what you will inject in phase with the current. So, thus real power required to be pumped, and thus what happen, you get a little higher voltage or less voltage depending on the compensation. For voltage swell compensation using UPQC Q, the quadrature component injected by the series connected voltage source converter DVR does not intersect with the voltage locus. You can see that. Therefore, Q cannot be used for the swell compensation. This is the one of the biggest difference, that you cannot, of course this is A and this is B. So, C square equal to A square plus B square. So, you never get C less than A. So, sag compensation is not possible in case of the Q compensation, but here you have you can inject in series or 180 degrees of the series, and thus you can change the directions of the voltage, and thus you can also compensate the sag. So, this type of operation of the UPQC is quite satisfactory for the voltage sag compensation, where swell does not come into the picture. However, it cannot be used for the voltage swell or the voltage buck compensation, and since DVR part of the UPQC inject only the reactive power, and this type of UPQC is also known as the UPQC Q, and the figure of the UPQC is P has been shown in the previous page. In UPQC P, the shunt compensator of this STATCOM used for all current based compensations at the unity power factor at the load end. So, this is the case. In such a situation, the series compensation DVR inject in series between the AC mains and the load end in the phase supply current and the supply voltage, and needs active power from the series VAC or the DVR. Generally, it is DVR without any reactive power injection through the DVR with minimum injection. So, ultimately if you inject in phase, generally A plus B, C is maximum when it is in phase. So, for this reason it is more effective vectorially. So, but it required to flow the real power, that is the challenge, thus the rating required to be higher, device rating required to be higher in case of the P type of UPQC. So, this is the current based, previously it was a voltage based, it was I, and now what happened, you inject the Vs equal to VL plus VL prime, and this is the DVR voltage in phase with the current, and ultimately IL will be in a same phase because you are just increasing the magnitude of the voltages. Same way, previously you can inject the DVR 180 phase shifted voltage, and thus it will come down, but the phase and current will remain same. we assume that it is a right shunt compensation. All the assumption of and our discussion is based on the right shunt. Left shunt we generally do not use it. The right shunt UPQC Q approach is limited to the compensation of the sag. Compensation of the sag in the system. The UPQC P can effectively compensate both voltage sag as well as the voltage swell of the system. Furthermore, to compensate an equal percentage of the sag, the UPQC requires a larger magnitude of the series injection than the UPQC P, because this is the case. So, this magnitude, and once you have in phase, this is the magnitude. Of course, this magnitude is better than this magnitude, but challenge of P is that real power required to flow from this D statcom in case of the sag compensation, and also the reverse, real power has to go out in case of the swell compensation. In this type of the UPQC P, the rating of the DVR is also quite low and requires a minimum series voltage injection. Since DVR part of the UPQC injects active power, this type of UPQC is known as the UPQC P, and this type of compensations of UPQC key is quite satisfactory for both the sags and the swell compensation. But it is a poor while you have a problem related to the poor power factor. There UPQC Q always perform better, and thus there is a middleman in the road, that is the UPQC S, that based on the KVA rating, and it has a flexibility, you can inject in any voltage. In case of the UPQC S, the shunt compensator D statcom is used for the all current based compensation other than full reactive power of the load or the source end. Now, what happened here? In such a situation, series compensation DVR inject a voltage in series in between the AC mains and the load end phase angle at the PCC. It is not, it is pre-calculated. So, what kind of voltage you require to inject? You will solve this problem on the assignment, what kind of angle required to be calculated. Based on that, you will set the angle for the injection. It need both active power and the reactive power through the series VSC. So, ultimately instead of this or this, you may have this, because you in case of the UPQC P you have this, in case of UPQC Q you have this, but accurately you require to this, that is not possible. Then we require to use the both UPQC P and Q together. Instead of that is merged, and optimal angle compensation can be obtained. It needs both active and the reactive power flow through the VSC DVR with the minimum VA rating with both voltage source converter. This type of operation of the UPQC S is gaining popularity and is quite satisfactorily for both sags as well as the swell compensation. If you have a more sag problem, then you use it as a UPQC Q mostly. Moreover, this type of UPQCS, the rating of the DVR and D statcom are optimized, and this is the optimizations of the rating, and thus you require the minimum BOM cost, something like that. So, minimize or utilize in a proper condition to supply reactive power of the system for proper sharing of this rating of this D statcom and the DVR. This flexibility is possible. So, let us see how does it operate. this was the current and ultimately you inject in this optimal angle. So, and thus the resultant load voltage become this after compensations. You had the angle between this in a phase, this is L, now you become the L prime, but you inject the DST and ultimately you come here. So, with respect to VL and IS, you got a angle that is delta, which is pre-calculated. Based on that, you will go to the injection. Same way here also, you inject the DVR voltage this to, if you want to have a sag compensations, and thus you require to also inject IDST, and thus you get a new delta, which is pre-calculated. So, what we can say here, the concept of the UPQCS with the minimum VA rating, we switch cost, the major cost here, unlike the patent cost and another thing in other industries. Rating of the VSC or the phase angle control, in abbreviation this is PSC, of the series voltage injection of the DVR has been introduced for different objectives. The voltage sag and voltage swell compensation with series voltage injection at a suitable phase angle with required objective has been fulfilled or can be achieved. That is what it has been shown here. One of which may be used to reduce the overall VA rating of the UPQC. And apart from that, since the VAR part of the UPQC injects the active and the reactive power with a minimum VA rating, this type of there is another name of it, this type of UPQC is known as the UPQCS, where S denotes for the apparent power, which is the VA rating optimization, optimized VA rating, that stands for it. Thank you. Thank you for your attentions. We shall continue our discussions of the power quality improvement technique in our next classes.